So, summary of images produced by converging mirrors. And just to let you know, well, what is the other name for a converging mirror? Which one is it? That's my question to you, as he wavers on the answer. Oh, nice. I like it. Good restraint. Yep. Concave. Bends in like a cave. So the converging mirrors, remember, are the concave ones, like that. And they're the ones that give us the interesting images. I have two concave mirrors right here. I'm hoping we can start a fire with one of these two when we go outside, when we're done talking about uses. But these are the ones that give us the interesting characteristics for the images. Again, hopefully if you can see yourself, I'm hoping, are you inverted? Logan, are you inverted? Can you see yourself in there? Are you inverted? Yeah, that's a weird one. This one has a little bit of deformations in it. This one's more curved, but it's starting to break down. I don't know if you can find yourself in that one. Can you find yourself in there? Hopefully inverted. All right. And that's what we want to talk about. And that's exactly what you guys did. So, I want to start here. By the way, this is where the object is. The object. And the very first picture that we did, if you take a look at your sheet right now, that long sheet, the top one, notice that the object is beyond C. The top picture. Do you see how the object is out there beyond C? And what I want to now do is I want to write a summary of those image characteristics for an object that's beyond C. So looking at your picture, you're going to tell me what's the size of the image when it's beyond C. Yep. Smaller? Small. Excellent. What's the attitude, Tyson? Inverted. Location. Where is it located? Cade, where is it located? Between C and F. Fairly close to the mirror. And what type is it? Jake? Real. Now, in a moment, I'm going to use a very bright light source as the object, and I'm going to show you what it means to have it be real. We'll talk about this in a moment. Now we're going to move the object into C. Size. In an ideal world, yep. Yeah, in an ideal world, the same. If you were able to have it be the same, that's awesome. You did very well with your raise. Attitude, yep. Still inverted. Inverted. Location. Where's it located? Got your picture? No. Yeah, you do. It's right here in front of you. See? It's right there. That's the one I'm talking about. We're summarizing this. Location of our. Where is the location of our image? Where is our location of our image? At C. When it's on C, the image is also at C. It's in the same spot. And what type is it? Yeah, Eric, what type? Real. It's out in front of the mirror. The real world is out in front of the mirror. The virtual world is in behind the mirror. Between C and F. Somebody rattle all four of them off instead of me picking and choosing. What do you got, Eric?
Bigger, inverted.
Hold on, slow down. Larger, inverted, beyond C, and real. Notice what's happening to the image as our object comes closer. It starts at C and F, then moves out to C, then moves beyond C. It gets further and further away. So when the object moves in, the image moves out. At F, what did we have at F, Tyson? No image. No image. No image. Those rays are parallel. They will never meet. We don't see an image. Within F, size. Yep, Eric. Larger or large, good. Upright. Behind the mirror. Behind the mirror. And virtual. Virtual. All right. Let me show you what that looks like. I'm going to show you a couple of things here before we investigate the other one. So let's take a look at this mirror here. Now, this mirror works really good for this demonstration. I need a very colorful object for you to see. I used to have a glue stick. That might work out okay. Ooh, that's a crayon that I write on the board with. Okay. So actually, you know what? Yellow is better. You guys can see yellow better. So I'm going to do this twice, all right? So what I'm going to ask you guys to do right now, and I need you guys to lean so that your head is in line with the mirror, okay? So I need you to lean in. I need you to lean to the center. All right, you might need to lean a little, even a little more there, Josh, to see this. Okay, so I'm going to put the pen out in front of the mirror, and I want you to find the pen in the mirror. Can you find the pen in the mirror? And is it upside down or is it right side up? It's upside down. So if it's upside, is it smaller or is it larger? Smaller. So where do I have the pen? Do I have it beyond C, at C, between C and F, or at F? Where do I have the pen? I have to have it beyond C because notice it's smaller and it's inverted. Can everybody see that? Can you see it? Okay. Now I'm going to slowly bring the pen in. And I want you to focus on the image of the pen. Don't focus on the pen itself, just focus on the image of the pen. You should see it start to move out towards you. And at some point, the pen should be right beside the image of the pen, and it should be the same size. And I want you to tell me when it's the same size. Can you see it? Better? It's about the same size? That means where is this pen if it's at the same size? It's at C. Now, this image is a real image. It's actually floating out in front of the mirror. If I wiggle the mirror, you should see that image move as if I wiggled the real pen. Watch the image. Are you seeing the image? Can you see it kind of move there in space? Okay. Now I'm going to keep moving it in. What's happening to the image? Is it going up? Yeah. It's going up because I'm not right in line. Is that better? Yeah. Disappearing-ish. At some point in time, it is going to disappear. Now, the image is actually coming towards you. At some point, Josh is going to say, I can't see anything. But Nolan at the back will say, whoa, this is really cool, it's really big, it's way out here. And that's because the image is actually past you. It's actually in behind you. So if you can't see it anymore, it's because you're sitting at the front and the image has gone past you. At some point, it's going to disappear completely. It's going to, some of you are going to be saying, it's huge. It's coming out at you. It's creeping you out. Good, it should be creeping you out. What's happening? Well, yeah. Yeah, that's right. I'm going to bonk you. Now, where is it? And it's behind it, right? So now where did I end up? I ended up in between F. Where was it when it disappeared? At F. At F. So I'm going to do the same thing. I'm going to do it for this row. So you guys have to get out of your chairs and lean over here. You guys got to get out of your chairs and lean over here. So you guys, if you want to see this, you got to get off of your chair and look in the middle. If you're visually impaired, I don't know, I can't help you. No, you guys, I'm not doing this the second time, so if you want to see, you actually got to get in line. No, not interested? It's cool. All right, find the pen. Did you find it? Is it upside down? Now I'm going to bring it in, and it's going to start moving out towards you. Is it at the same size yet? I should be close to C. So now as I move in, the image is going to come towards you. Focus on the image, not on the pen. Is it big? Now at some point, Tyson, you're not going to be able to see it anymore because it's going to go past you. Can you still see it? It's huge for you probably, like right in your face. For Max, he's not seeing it so huge yet because it's still way out there. Tyson, huge? Can you even see it anymore? Impressive. At some point, it's going to disappear. Max, what are you seeing out there? Again, like I said, it's a real image. It's out in front of me. If I wiggle the mirror, that pen does some weird things. At some point, it's going to disappear. Like the mirror will be full with yellow. Is it? Mirror full with yellow yet? All right, and then if I get closer to the focal point, now you've got to actually probably look behind the mirror to see the pen. Can you see it? And it should be huge. And it should be right side up. So in the end, that image comes out at you. Let me show you the thing before we talk about the other one. First, I'm going to shut this off. Question? Yep. Yes, that's what I'm going to do right now. So instead of using a pen, I'm going to use a lamp. All right? So the lamp's going to have a light source in it, right? And I'm going to put it on the wall. Now the same thing is true, right? Now, take a look at the wall right there. Can you see it? What is that on the wall? And what is that the letters of? The print on the bulb. Can you tell how strong this bulb is if I get it focused right? What is the strength of that bulb? How many watts?
180.
It's a 150. So I can't get it perfectly clear. But you can see that's definitely a real image, right? That is definitely a real image there because I can put it on the wall. I can project it. You see that? If I bring it really close, now you can see the light bulb in the mirror, but I can't see the light bulb on the wall. You have to look in the mirror. If I bring that back out. Another benefit is, if you look over at me, right, another benefit is I can blind you guys completely, like this. Whoa. You okay? Whoops. Whoa. All right. Sorry. Oh, my goodness. Everybody awake? Sorry about that. No, I'm not sorry at all. That's just fun. Let's take a look at this one here. This has a different focal length, so I'm going to get a slightly different situation, but let's see if I can get it on there too. That one's smaller. See how the writing is smaller? And also, it's not as defined because this mirror has some imperfections in it. If I were to take the sun's rays and focus it on the spot instead of a little lamp, if the sun's rays are more powerful, I might be able to get something to burn, right? Start it on fire. So that's what we're going to try to do. Okay. Let's talk for a moment. One last thing. Okay, we've done diverging. We've done that. Now, put summary of images produced by a diverging mirror, but don't make that chart. Don't make the chart. Just write down summary of images produced by a diverging mirror. And don't make the chart. I don't even know why I put that chart in there. That's just kind of mean. Because in the end, I don't know if you remember, but on Friday at the very end, we did one image for a diverging mirror. We did one. And I only need to do one. Because it doesn't matter where I put that object for a diverging mirror, its characteristics are the same. All right? So it doesn't matter where we put it. So what I'd like you to put is just put one salt. It doesn't have to be down, it can be across. the image characteristics for a diverging mirror are always the same? Well, if you can't find your picture, well, you should keep better notes. But you tell me, what's the size of your image in this mirror? It's not the same. Not even close. Smaller. Smaller. What's its attitude? Upright. Now, its location. Yep. Nope, not the same. No, it actually isn't further. It is closer. It's between F and the mirror. Between F and the mirror. And type. Where do you have to look in order to see this image? Into the mirror. It's in behind here. So if it's in behind, what type is it? Virtual. Virtual. Diverging mirrors are not exciting in any way. Because number one, their images are all the same. I'm not going to be able to start a fire with this thing because it's not going to concentrate the rays. What does it do with the rays? What's that? It doesn't absorb the rays. Yep. Spreads them out. Spreads the rays out. Those rays are spreading out. So I can't notice if I get the mirror in there, it actually makes the wall darker because I've spread the rays out. The rays are now less intense than if I just shone the light at it. I've actually made the light rays less intense. Okay. Let us continue now and talk about uses for curved reflectors. And then when we're done this little note on uses for curved reflectors, we will go outside and we will attempt to burn a piece of paper. And then, like I said, we will watch a video on the Mythbusters, and those people who aren't done can work on finishing off. So first things I'm going to talk about are concave reflectors, because the concave ones are the interesting ones. Solar collectors. I actually had a device like this. I've been running around the school trying to find it, but I don't know where it went. In this solar bowl is what we call a Stirling engine. Stirling is simply named after the scientist that kind of created it. A Stirling engine is almost like an internal combustion engine, but instead of burning fuel, it just uses hot air. And this solar collector would concentrate the sun's energy on the tip of that thing, which then contained the air within it that when heated would run this little engine. It's called a Stirling engine. Because the rays are parallel, because the sun's rays are very far away and they're coming in at parallel, where do I have to put the thing that I want to heat? Where do parallel rays meet? Yep, the focal point. It says it right there. The object that we want to heat has to go at the focal point because those parallel rays will meet there and we'll get it really hot. And if the sun's rays are hot enough today, hopefully we can get a piece of tissue paper or something to burn or maybe smoke. But in the fall, sometimes it doesn't work very well because the sun is so low in the sky that the angle at which the sun rays hit us are not as intense as it is during the summer. We all know that, right? The sun doesn't seem to be as hot. So, solar collectors. Put the object to be heated at the focal point. I am going to draw a little picture here, and I'm going to ask you to draw it. Just draw this here, like this. Put a little back on it. Just make it a sketch. It doesn't have to be fancy. And we will put 3 rays. There's a ray coming in, coming out. This ray coming in. I'm going to have it hit right there. This ray coming in. I'm going to have it hit right there. And so I'm going to put an F right there. Ray in, ray out, ray in, ray out. We want to put that thing at the F in order for it to get really hot, collect that energy. There are solar electric plants that they've created massive mirrors that are all on a slightly different angle, and they're out in like a field, like a 100-acre field, and they point that sun right at a focal point, which is in a building that then heats a fluid, which then used to boil water and drive a turbine, and they create solar energy out of that. Massive solar collectors, like massive mirrors. Okay. What else can we use these things for? Satellite dishes. Your satellite dish is similar to that. Now notice I found some images of some good old school satellite dishes. When I was a kid, that's what people had in their backyard, an actual big dish pointed at one satellite, and each satellite would give you like 2 channels. So then if you wanted a different set of channels, the satellite had to move and find the next satellite, which carried 2 or 3 channels. Now, the technology is so well that each satellite, like each company, say it be Rogers or Shaw or whatever, contains all the information and all the channels, so you don't have to move the dish anymore. But years ago, you had to move the dish. Here we've got a great big radio telescope dish, that picture down at the bottom. That's used for maybe imaging radio waves coming from various stars or various objects. Here we've got a classic little dish. This is an old one. Now they're more elliptical. You'll notice they've got a little bit of a curve to them. They're not like a complete circle. You don't have to move them because they're always pointed at that satellite. All right? And the satellite, it may be moving, but it's at a particular orbit that we call geostationary. In other words, its orbital speed is the same rate at which the Earth rotates. So as the satellite is in orbit, we on the Earth are rotating underneath it at the same speed. So all you got to do is point it at it. You don't have to adjust it unless the wind blows it out of whack, right? But again, the rays would be coming in, and they wouldn't necessarily be coming right there. Notice how the receiver is off on an angle, and it's not right at the focal point. That's because the actual satellite is up here somewhere, and it would be bouncing its rays off to that location there. It would be designed to bounce its rays off to the receiver, and then the receiver would be at a place where all those rays are coming in. So it doesn't necessarily have to be pointed right at it because they're bouncing and reflecting and doing a similar thing. But we're just using radio waves instead of light waves, right? So just like your radio tunes into a radio, they've got not a beam, but a signal of radio waves that are then focused. So satellite dishes work the same way. All right. For producing parallel rays. So sometimes we want to produce a beam of parallel rays. And that's what you do with a flashlight or a headlight. Put the light source at the focal point. Now my rays are heading this way, out and out, out and out. This one goes in and comes out. Sometimes they're called a spotlight. You know what I mean? Like those spotlights. Or those great big hunting lights, which you're not supposed to use because you're not supposed to use lights. You wouldn't do that, would you?
No, never.
Oh, okay. But, you know, they're nice and bright because they've got that right at that focal point. They produce that beam. You just use it for good, not for evil. So by having the light source where the light rays are coming off of that lamp, yes, the light that's coming out the front is still heading out, but any of the light that's heading back will also head out. You get more of the light pushed out in front of you instead of like a regular light bulb that it's spreading out. Again, if you want to draw that very simply, just draw yourself a simple little mirror with the rays heading out from the focal point. It's kind of like the opposite of the solar collector. You're putting a light source at F, and it's pushing it out. Okay. Other uses for concave mirrors, shaving/makeup mirrors. All right? and they are concave, all right? And in order to get the big upright image, you need to put your face within the focal length. So you've got to get fairly close, like this. Like this? See? See, like this? Right there? No? Nothing? You're averting your eyes? That's funny stuff, isn't it? No? Here, you want to check it out? Ooh, that's fun. No? Who wants to see it? Who wants to have their face within the focal length? Yes, I'm sure Nolan definitely did. That's just fun, isn't it? Just huge. Want to take a look? Whoa, that's good stuff. Nice stuff. Nice. Right? See, I usually do this type of thing, and hopefully there's not too much ear hair going on there. You might be able to spot that, Tyson. You know? Am I doing okay? Did I trim appropriately? Obviously, in a makeup mirror, the curvature isn't as great. The greater the curvature is, the bigger the image is. Right? You can see that one's got a greater curvature, so it's even bigger. Right? So the greater the curvature. So on a makeup mirror, it's just a tiny little curvature. It just makes it look a little bit big. So the focal length is really long. So you flip it over, right? And it looks the same. You flip it, it's a little bigger because it's just got a little bit of a curvature to it. So put your face within the focal length and it will make a larger upright virtual image. You can see that. So that's how those mirrors work. And one last one I think I've got here is what we simply call wide-angle mirrors. Really only one use for diverging mirrors. They're wide-angle mirrors. And I don't know where everyone is at writing. Whoops. Whoops. Oh, my goodness gracious, are you kidding me? Just blew up one. Wide-angle mirrors used for looking around corners, like in hospitals, used for the wide-angle mirror, say on your car, on a truck, right, so that you can see into the blind spot. The front of a bus has got a really convex mirror so they can see, make sure there's no kids in front of the bus. Yep. Yep. Yeah, I don't see them a lot here. I've seen them in places like, small town Quebec where you'd go skiing, say, and the snow would be piled high. They have a stop sign. They've got a mirror so you can see around the corner, make sure nobody's coming. I've been to Europe where some of those tight roads, right, where tiny little roads and you can't see, so you got to use the mirror. Yep, you bet. So in stores, in hospitals, where you're trying to run around a corner with a person on a gurney and don't want to run into anybody, et cetera, used on vehicles, you see that type of thing so that they can see into their blind spot, et cetera. Okay, so there are some uses for curved mirrors, and I am going to just stop my recording here for a moment. And like I said,